Hello and welcome back to another neural net and TensorFlow video. My name's Ian, and today we're going to talk about optimizers. Now, previously up to this point, all of our optimizers we've been using is just standard simple gradient descent. So we calculate the partial derivative and then we multiply by our learning rate and shift our parameters that way. This is a very simple, easy way to do it, but there's a lot of problems that can happen in practice. So the first thing about gradient descent is very slow. It's going to take you a long time to converge on our global optimum. But the other thing is we can also run into kind of local minimums, I guess you could say. So that's when we're going down a hill, we're calculating the gradients going this way, this way. We get up to here, instead of going in this direction, we're going to actually go back down. And we're going to kind of oscillate in this local minimum, and instead of going into the one we want to go. Now the way we're going to try to avoid this is we're going to use momentum. And momentum is very similar to kind of like the physics problem, where basically picture like a ball rolling down the hill. As it's rolling down, it's going to gather momentum, and instead of getting pushed back by gravity, the momentum is going to kind of carry it over this hill and then roll back down. And this is how we're going to avoid local minimums. So how do we do this? Well, we're going to calculate the velocity. So velocity at our current time step is going to equal the velocity at our previous time step, and we're going to add the partial derivative we got at weight 1 or something like that. So let's do delta weight I. Okay, then we take this. So let's go weight I, and we're going to plus equal the weight we got, our velocity, I guess we're doing. And then we're just going to multiply by our learning rate. So instead of just using this partial derivative, I guess you could say, and then multiplying by our learning rate, we're going to actually add the previous velocity we had. And then the next time, this is going to be t minus 1, or t plus 1, and this is going to be t minus 1 or whatever. So we're going to constantly store this variable and update it with our previous velocity. If it's a little confusing, that's probably because it is. So let's do this kind of in like a geometric kind of way. Here's our point we're going to. Here's where we are. Now we already have a momentum carrying us this way, and we're going to calculate the gradient here. Okay, and then we're going to add these two vectors. And here's going to be our update one. So you can see we're taking a much larger step, this one, but it's not quite as accurate, but that's okay. So now we're at this point now, and we're going to take this variable, that's going to be our momentum, this is the same thing, and then we're going to calculate our gradient from there, or our gradient, and then we're going to add it again. And we're going to add these two vectors, and kind of like that. So this is kind of how momentum can work, and we kind of just keep doing that until we get to the end. Now, the problem we saw is that it overshoots it. So it was kind of points there, or we might end up going like this, over kind of shooting it, and then kind of go back. The way we can adjust this was another kind of form of momentum, and this is Nesterov's accelerated gradient. So very similar to the momentum. The only difference is this time we're going to calculate our gradient after we push our momentum forward. So we're at this point, and we're trying to go here. We take a momentum, and instead of calculating our gradient here, we're going to calculate our gradient after we've done the momentum. And this is going to be our new vector. Okay, so but let's imagine if we're doing momentum, it might be like that. And well, it's a little confusing right now. hopefully you can kind of understand why we're adjusting back with our gradient instead of just standard momentum. So okay, maybe I'll try and show you. So here, here, and these are going to be the same thing. I'm going to do momentum up here and then Nesterov's accelerated gradient down here. So let's do like that and then that. So these are equal length in the exact same direction. I'm trying my best, but probably not really. So in momentum, we calculate our gradient here. It's kind of the direction where it's supposed to be headed. And then we're going to calculate our, add these two vectors together, and we're adding that point here. Now if we do Nesterov's, we're going to calculate our gradient here. Hopefully those are the same length. I think that one's a little shorter. And that's going to be our point there. So you can see, still didn't do too good of a job, but hopefully you can understand that what Nesterov accelerated gradient is trying to do is kind of, I guess, correct the gradient as it's during the momentum process, I guess. I don't know. Okay. Okay, so the next optimizer we're going to go through is Addigrad. And Addigrad is our adaptive gradient one. So what you'll see when you look at a loss function, you might find something looks a little something like it's described as kind of like a taco shell. So what this has is a very slight kind of downward trend in the horizontal direction, but very steep ones in the vertical direction. And it kind of, yeah, no, creates like a half pipe or something like that. So if we're at this point and we're calculating the gradient, what's going to happen? It's going to kind of go like this and all the way to the bottom. But what we want it to do is just kind of go straight down. Now how we're going to do this is if we get those, let's go, these large gradients, we want to punish them and shrink them in that direction, and keep the smaller gradients relatively unchanged. And this is going to give us a more optimal path. So how we're going to do this, we're going to get a variable g, just naming that, and this is going to be a running sum, so it's going to be plus equal, and what are we going to add? We're going to add delta g sub I. Actually, I should do that. So we calculated our partial derivative at whatever dimension we're at, and we're going to square it and then sum it into one variable. Then what we're going to do, we take this variable and we're going to divide our learning rate by it. Okay, and then we just do the standard thing we just do with the learning rate, and we multiply our gradient by that. Make this negative, and then we update whatever our parameter is, weight sub I or something like that. So what this is going to do, as we go along, g is going to get bigger and bigger and bigger. We don't have any negative gradients because we're squaring them, so automatically it's just going to keep growing and growing and growing. Now, actually, there's an epsilon there, just to kind of, it's a very small number and you just divide by 0, but so what's going to happen is this g is going to get bigger and bigger, and when our denominator gets larger and larger and larger, actually, I forgot, oops, this is square root as well. Our denominator is going to get larger and larger, so our learning rate is going to get smaller and smaller. So say this is a huge number, we're dividing by 0.01, we're going to get a very small number and multiply that. So we're going to take very small step sizes. So basically what it's doing is kind of shrinking our learning rate. And this is kind of, if we go back to this, it's going to take very large gradients this way and kind of shrink them down, and then we can kind of get a nice little path out there. Now, what's an obvious problem with this? Well, G is going to keep getting bigger and bigger and bigger and bigger. There's nothing that's going to stop it. So as we already said, it's going to shrink our learning rate. So what's going to happen? Our learning rate is going to get smaller and smaller and smaller. It's going to get close to zero as possible. And our step size is going to be basically nothing. And this is absolutely something that can happen in practice. What happens is you're training, and it looks like it's stopped, and you might think you have a problem with the gradient, but basically your learning rate is just close to zero. So this is a problem with Atagrad, and this is why it's rarely, if ever, used nowadays, because we have better ways of dealing with that, and we're going to do that with AdaDelta. Okay, so what AdaDelta does is it fixes that kind of vanishing learning rate problem by not by trying to like degrade the amount each stored gradient has. So let's see if that can make sense. So we're at G parameter I, and I'm just going to do time step t. So this is where we're at in the training process. And what we're going to do is get a hyperparameter, gamma. I think that's gamma, I'm not sure. And we're going to multiply that by our previous stored gradient or whatever. So this is at G I t minus 1. Okay, so this is going to be about 0.9 or 0.99, so it's going to kind of shrink the effect of previous gradients. And then we're going to add that, and we're going to go 1 minus y, or gamma, sorry. So if this is 0.9, this is going to be 0.1 or something like that. And we're going to multiply that by whatever parameter we're at right now. So delta wi, sorry I ran out of room. This is a dot multiplying delta weight at I. Okay, and this is what, oh sorry, we're going to square this as well. And this is what we're going to do instead of just kind of doing the plus equals thing. So we got our learning rate, and we're going to do divide by the root gi at t. And we're going to add our epsilon to prevent dividing by 0, and then do our standard parameter we're doing update there. So this is AdaDelta, very similar to Atagrad. It's just we're adding in that gamma parameter. So okay, now so we had advantages of our Atagrad. We've seen advantages of our momentum. Now you might be thinking, well, they don't kind of cross over, so why not both? And that's exactly what Atom is. So instead of we're doing, Atom is adaptive momentum. So basically we take the momentum, we do our learning rate times our velocity, I guess. Remember, our velocity and momentum was our velocity of previous one, and we add the gradient to that, and we're going to do divide, and that's going to be our GIT or whatever like that, or whatever we did in AdaDelta. So I'm not really going to go into much into Atom because it's kind of just momentum and AdaDelta kind of divide or combine. So I don't think there's too much need to describe in details. I'm going to show some code of how it is, so maybe it'll be easier to find out. That's basically all the optimizers. You will see NATM, which is kind of a Nesterov adaptive momentum, and it uses the Nesterov accelerated gradient instead of just standard momentum. This is rarely used, and I don't know why. But yeah, everyone just kind of seems to use Atom. So if you're looking at which optimizers you should use, people are going to say Atom. I'd use NATM, but again, I'm the only person who does that, so I'm not really sure why, but I don't know. And there's actually a new one that just came out. It's AMS Prop. Kind of came out like 2 months ago, and hasn't really shown really great improvement over Atom. So as of now, I'm just going to suggest just choose Atom. But that's all you can really get out of this video. But okay, I'm just going to go into some quick visualizations though.